ready to begin chapters 8 and 9 in your text. I've been grading some of y'all's labs, so I know that some of you have already done the lab that's associated with this, so this may be just a review, maybe a welcome respite from this. And we are going to kind of combine these two chapters, and we are not going to go perhaps into the depth that Dr. Burdg seems to enjoy going into. A lot of the material that's in this chapter is Chem 2 material. So you would talk about this in the second portion of this text, of this course. But a great deal of it is we've already covered and kind of makes sense and goes right along with chapters 6 and 7. And a lot of you have already done it because you have done the lab, the one with the molecular model. So you've already kind of done the dots and the Lewis dot structure, so you kind of already know some of this material. So we're going to just begin. And so let's talk about what a Lewis dot symbol is. You already know what a valence electron is. A valence electron are those that are in the outermost energy levels, and those are the ones that deal with bonding. So those are the only ones that we need to really worry about, because we know that the lower energies electrons, they're already full, completely full, so they're stable. Not much change is going to occur with them, because if it did, that would bring instability to the atom, and it's not going to do that if it possibly can help it. So Gilbert Lewis came up with this, and he said that atoms want to become as much like a noble gas as they possibly can. So if they can become isoelectronic, that is, if they can have the same electron configuration as a noble gas, that's going to make it the most stable, and that's exactly what they'll do. So when atoms gain or lose electrons so that they can become like a noble gas, it is those valence or those outer shell electrons that interact. Those are the ones. So if we could figure out a way to show those electrons and how they interact, that would be a good thing, and we wouldn't have to go about drawing pictures and those kinds of things. We could come up with a more simplistic way, and so Lewis came up with what he called his Lewis dot symbol. And in his dot symbol, you've already seen this, like I said, if you've done your lab already. His Lewis dot symbol consists of, let's talk about calcium. You would have this symbol for calcium, and because calcium is a alkaline earth metal, that is a group 2A metal, that means it has two valence electrons. So you would show its two valence electrons. You could show them, because they aren't going to stay together if they can help it. You could show them on opposite sides of calcium, or you could show them paired, show them as two dots. Regardless, you're going to show that it has two and only two valence electrons. So this would be an electron dot diagram, an electron dot symbol for calcium. Alright, so it shows you here on this periodic table your electron dot symbols for your representative. And remember what a representative element is. A representative is one whose outer electrons are in the s or the p orbitals. The group 1A's, 2A's, or if their group number ends in an A, like, see these group letters, A's? These are called your representative elements. They're the most active ones, and then, of course, the noble gases. These are the elements that are going to be your most chemically active, closest to becoming like a noble gas, and so they're the ones that are going to be most important that you learn how to write. They're Lewis dot structures, and they're pretty simple to do. You just simply take how many valence electrons they have and put that many dots around there. And usually you can pair them up. If they have more than 3 or so, you'd pair them up Of course, now remember that electrons, they want to stay as far away from each other as possible. So if they only have 2 or 3, then you put them on all sides. And some people like to, if they have 4, put 1 on each corner, which is fine, as long as you're representing that it has how many valence electrons it has. Okay? So what about these if it's become an ion, like fluoride? So if you have the fluoride ion, now this is an ion, recognize that it is, if fluorine becomes an ion, what does fluorine need to do to become like a noble gas? Fluorine is number 9. What's the closest noble gas to number 9? It is neon, number 10. So fluorine is a halogen. Halogens tend to gain 1, so it's going to gain 1 electron. So whereas fluorine had 9 electrons, fluoride has 10. So that's going to make it isoelectronic with neon. So whereas fluorine, here's fluorine, it has only 9 electrons, whereas fluoride has 10. Here's your symbol for fluorine, and you're going to draw its 8. It has 8 valence. It has 2 in the first energy level and 8 in the second. And then to show that it has attained its noble gas configuration, you're going to put the normal noble gas brackets around there. And because it has a charge of -1, you're going to have to put its negative sign there as well. So this is fluoride, and then you ought to be able to do those others as well. Potassium has 1 valence electron already. When it becomes like a noble gas, it's going to lose because it's a group 1A metal, and metals tend to lose to become like a noble gas. So when you draw its ion, you're going to show it with no valence electrons, because it's lost its 1, and it's going to become isoelectronic with argon. Sulfide needs to gain 2 to become isoelectronic with argon, so you're going to show it had 6, it's going to gain 2 more, so you're going to show it with 8. Alright? So here would be what you would put. I would ask you to do one thing on this. I would disagree with Dr. Berg on this because I believe that this here, potassium, has also attained noble gas configuration. I believe you should have your brackets around it as well to show that it's become like a noble gas. Okay? All right, let's move on. Okay, we're not going to talk too much about this lattice energies too much, but we are going to mention it. But let's talk about ionic bonding, referring to electrostatic attraction. That electrostatic means that opposites attract. Okay, and we already know that opposites. You got to think about the fact that that attraction comes because the positive and the negative are attracted to each other. You know, in the case of the example that you have here, potassium and iodine, for example, potassium wants to lose that electron to become isoelectronic with argon. Iodine needs to gain 1 electron so that it can become more like xenon, that noble gas. And so it's going to gain 1 electron. When it gains 1 electron, it's going to become negative. When potassium loses its 1 electron, it's going to become positive. Well, when those take place, they may not take place at the same time, but now those opposite charges are going to be attracted to each other. And that is an electrostatic charge, and that's a very strong, very strong bond that's formed, and that bond is called an ionic bond. Okay, and that electron getting transferred, it is not shared, it is totally transferred. Potassium transfers its unwanted electron to iodine, who keeps it forever. Even if those two part ways, and they do, oftentimes do, then iodine doesn't give the electron back. It keeps it so that it can stay like that noble gas, and so that potassium can also remain isoelectronic with argon. And so here is the Lewis dot structures for this process. Potassium losing its electron and becoming potassium ion, and iodine gaining an electron and become the iodide ion. And then those two coming together. And then these last two pieces of information down at the bottom, the ionization of potassium taking in 419 kilojoules per mole of energy. That's how much is required. And then you have the electron affinity of iodine. Now, we are not going to focus quite so much on these numbers, as we are going to be concerned with the process of this happening. So then it talks about, you would see that it requires energy for this to happen. You have to add energy for this to occur. Now, usually when you have to add energy for something to happen, well, if it costs energy, just like, your dad or your husband or whoever, if it costs money, well, we're not doing it. But in this case, you're going to notice that a lot of times when the bond is formed, it's very exothermic, so that means it gives off energy after the bond is formed, and so that giving off energy outweighs how much energy it costs to form the bond in the first place. So it costs a little bit of money up front, but you make a lot more in the end, so it's worth the investment. That's how it kind of works. That's what it's talking about right here. Okay? And that's what it's talking about. We can quantify this energy change, and that's called lattice energy. That's what the name of that is called, lattice energy. So we're not going to do too awful much with lattice energies, because they're, like I said, more of a Chem 2 topic. But here is the lattice energy of potassium iodide. That's a significant energy release. Okay, and there's some more that it's talking about right here. And these are some beautiful slides that it's given here, but we're going to more focus on would we have to gain or lose electrons, and how many, and let's draw these dot diagrams and see how bond energies are formed and things like that. I do want you to pay attention here. If you have something like lithium fluoride, each one of them need to lose one. You have a smaller lattice energy than you would if they need to lose and gain two and things of that nature. Okay. This is called the Born-Haber cycle, and it's kind of going through the steps, each step in the process of, here's sodium chloride, and the steps that you go through to make it, and is it worth the energy process to go through. But that's as far as we're going to go in this course. Here's where we're going to spend most of our time. Lewis structures. When he's talking about his Lewis theory of bonding, again, this is the same guy that came up with Lewis dot structures. Gilbert Lewis suggested that a chemical bond involves also sharing electron. This is the Lewis theory of bonding, so we're talking about covalent bonds now. This is, please keep in mind from, what was it, chapter 2 or 3, where we talked about ionic bonding versus covalent bonding, and that covalent bonding occurs between two non-metals. So please keep in mind, last chapter we split the periodic table up into metals, non-metals, and the metalloids. And that metalloids are those zigzag kind of staircase that's to the right and on the periodic table. And there are most of the elements that are on the periodic table are metals. And a few on the upper right corner plus hydrogen are non-metals. So keep that in mind. And these non-metals, they need to gain electrons to become like a noble gas. And so if they need to gain electrons already, they're not going to be willing to give one up and transfer one to someone else. But they would be willing to share. And this is what Lewis said. So notice what here is going on in this particular slide. Two hydrogen atoms, they move close enough that they're willing to share their electron pair in between them, and thus both of them are feeling the effect of two electrons. They're feeling the effect of two electrons because it's shared in between. So each one's feeling like it's got two electrons, so that it's feeling like it's isoelectronic with helium. So this type of arrangement is called covalent, and the bond that they make by sharing this pair of electrons is called a covalent bond. Now, a lot of you that did that molecular bonding lab already understand this, or already have seen this at work when you were playing with those molecules, and you could see that each one shared pair, a shared pair is two electrons. Sometimes that shared pair can be one from each atom. Sometimes it can be they both come from the same atom, but both of the elements are sharing that same pair. So that forms a bond between the two atoms. All right. Here's what he said. He came up with what he called the octet rule, and octet means 8. And there's also called a duet rule for helium because he can only hold 2 electrons. So ones like helium, hydrogen, they can only hold 2 electrons because they live in the first energy level, and that energy level can only hold at most 2. So the octet rule for every other energy level, first energy level, the duet rule. The octet rule says that atoms are going to gain or lose or share so that those atoms can achieve a noble gas configuration. In this case, we have fluorine. Fluorine has 7 electrons in its valence shell. It wants 8. If it cannot find some place to get an extra to take or to have one transferred to it, and it will be willing to share an electron with someone else. Now let's keep in mind something about fluorine. It is the most electronegative element on the entire chart. It's highest up on its family and farthest to the right. So it's the smallest, and you know small things are sometimes the biggest bully. So fluorine is by far actually the most electronegative element that there is on the chart. So if it's paired with something else, it's not going to share fair. So please understand that. But if it's sharing with another fluorine, then they're going to share 1 electron from each one in between, and that's going to make a bond. And then you have all these extra electrons that are not shared around them. And these are called, if you've done the lab, these are called unshared or lone pairs. All these 2 electrons that are not shared with anything are called lone pairs. These that are shared in the middle make the bond. It makes a covalent bond, and we represent that bond with a line, a single line, for just 2 electrons. If there's more than 2 being shared between the 2, then we would represent it with 2 or more lines. Right, and this is the case of water right here. We have H2O. Notice a hydrogen just needs 1 electron so that it can be isoelectronic with helium, but oxygen needs 2 electrons. So it is going to share with two separate hydrogen atoms, and therefore we get this shape or this configuration of hydrogen sharing one electron here, and this hydrogen coming in and sharing with an electron on this side. And so we have two unshared pairs or lone pairs here. Okay, and then here's your fluorine, and then there's your water. And notice what it says at the bottom. The octet rule is going to work best for elements that are in periods 2, and they're just going to work much, much better. And we're going to discuss why that is, and because when you get into period 3, you get your D level elements. Your D level orbitals are involved, and they kind of get in the way of things. So they cause a little bit of trouble. Okay, we talked about this just a minute ago, but know what a single bond is, know what a double bond is, know what a triple bond is. A single bond means that you have two electrons being shared between the two atoms. Double bond would mean you have a total of 4 electrons being shared between the two atoms, because a bond means you have 2 electrons that's being shared. A single bond means 2 electrons. So a double bond would mean 4 electrons that are being shared, 2 pairs. So here's a representation of a double bond, total of 4 electrons. Notice how they put the lone pairs, or the unshared pairs, kind of at angles, because electrons are negative. They don't like each other. They repel against each other, so they want to stay as far away from each other as possible. And so they push away. And that's why you get these particular configurations. If you need help with these, you really do need to pull out your molecule sets, and they have those kind of flat fan-shaped things. Those represent unpaired electrons, 2 unshared electrons. And then a triple bond. Remember, you're trying to get each atom to feel 8 electrons. That's the goal. You have to move the electrons around in order to feel 8 each one. You want it to feel 8 in the octet rule. There are a couple of exceptions, but that's the goal. All right? Now let's talk about bond length just for a minute. Now, Dr. Burdg is a numbers woman, and she really likes to talk about bond lengths and things like that. Now, what I care more that you know about is that the longest and weakest of the 3 is a single bond. I hope that makes sense to you. If you have 2 electrons that are being shared between 2 atoms, they're going to be not as strong, and it's also going to be a longer distance between the 2 atoms than if you had 4 electrons. That's going to be a stronger hold. And if you had 3 pairs of electrons being shared between 2 atoms, a triple bond, that's going to be pull the 2 atoms closer, tighter together, so the bond length between the 2 is going to be even shorter and much, much stronger. Now, I would expect you to know for sure this, comparing ionic and covalent compounds. I often ask my in-class students to write a paper here, a paragraph or 2, to compare the 2 and ask themselves, put yourselves in these 2 places. If you had to choose between ionic and covalent compounds, put them in terms of people. Which would you rather be? Think about it. Ionic compounds are at room temperature. They're mostly solids. They're very sturdy. They're when they are poured into water, they break apart and they conduct electricity. They have very, very high melting points. On the other hand, covalent compounds, they, when they are put into water, they don't break apart. Think of carbon dioxide gas. That's how sodas are made, is they bubble carbon dioxide gas through the syrups that we make our sodas from. When you put them, they are mostly gases at room temperature. So they're free spirits. So they have extremely different properties from each other. And it is because of how their molecular bondings are attained. Ionic bondings happen because of that positive and negative attraction for each other, whereas covalent bonding occurs because those electrons are being shared between the two bonds. And so those intermolecular forces between them are quite different, actually. And it gives you, I'll let you read on this, but molecules are just not as tightly held together as ionic compounds, and that's why ionic compounds have a much higher melting and boiling points than molecular compounds. And yet, molecular compounds tend to stay together when they're put into water, so they don't dissociate from each other when they are put into water like solids do. So if you are a freer spirit, maybe perhaps covalent are going to appeal to you more, but if you're a solid, that ionic might appeal to you more. Okay. These are a comparison of sodium chloride, table salt, and carbon tetrachloride. So a very ionic compound, table salt, and a very covalent compound. Very different properties. All right, that's good for this video.